Through our deep dive in atom theory, we learned that the flow of electrons or charged matter in general is called an electric current, while the pushing force behind it is called voltage. Now, we will learn about the relationship between the current and the voltage, which is called the resistance. Further, you will get to know the first component, the resistor.
This video is brought to you for free thanks to JLC PCB, the go-to platform for PCB prototyping and manufacturing. I've been using JLC PCB ever since I started designing PCBs, and it's been an incredibly seamless experience. What keeps me coming back is the convenience. They make it simple to upload your designs, choose your specifications, and get professional quality PCBs delivered. Whether you're creating your first PCB or pushing the boundaries of an advanced design, JLC PCB is a trusted partner you need. Check them out at jlcpcb.com and see why so many makers, including myself, rely on them.
We can think of the resistance as the diameter of the water pipe. As we established previously, the flow rate will be higher the higher the water level difference is. However, there is a second constraint, which is the diameter of the pipe. The smaller the diameter, the less water will flow. In electricity, the water pipe diameter analog would be the resistance of the conductor. The current and the voltage are in fact proportionally linked through Ohm's law. R is equal to U divided by I, and R is given in ohm. U is the voltage in volts and I is the current in ampere. Almost every component, even a conductor such as a wire, has some resistance. A wire without a resistance would be analogous to a tube with an infinite diameter. Often, the resistance is so small that it is neglectable. Nevertheless, in some cases, we want to limit the flowing current of a circuit intentionally. In this case, we have to introduce the resistance on purpose and have to use our first component, the resistor. A resistor provides a specific value of resistance. It is often made out of a carbon composition that is partly conductive and remains relatively constant in resistance over a wide temperature spectrum. The carbon composition is covered in plastics for isolation, and 2 leads are added for easy implementation in a circuit. Further, they come with color rings that represent the resistor's value. They have a total of 4 to 5 rings, while one ring is slightly spaced further apart than the rest. We always read the rings from the left so that the further spaced ring is on the very right. The first 2 to 3 rings represent the digits of the resistor, while the second last ring provides the multiplier and the final ring provides the tolerance, usually either plus minus 5% or plus minus 10% of the resistor's value. The final format is xx times 10 to the power of x plus minus x. To represent how different components are connected to form a functional electric circuit, we use something that is called a schematic. Every component has its dedicated symbol. A resistor, for example, is represented in this way. There are 2 different symbols for a resistor, one is used in Europe and one is used in the US. We will use the European symbol for the rest of this course. Something that we will need in every schematic is the voltage source. Usually a standard battery is represented by this symbol, where the longer line represents the plus pole. We connect different components by drawing lines between them. Just like that, we set up our first schematic of a resistor powered by a battery. Let's calculate the current in the circuit. Let's say we supply a voltage of 9 volts by the battery, and for the resistor we choose one that has 4 rings, a brown, black and a red one on the left and a gold one on the right. Brown stands for a 1, black for a 0 and red for a multiplier of 10 to the power of 2. So we have 10 times 10 to the power of 2, which is equal to 1000 ohms. The gold ring represents the deviation, which is plus minus 5%, so we expect the resistance value to be within 950 to 1050 ohm. If we want to know how much current is flowing in our circuit, we have to reformulate Ohm's law to output the current. I is equal to U over R, which is equal to 9 milliamps. So a voltage of 9 volts over a resistor of 1000 ohms results in a current of 9 milliamps. Now let's create a test circuit. This time we supply a voltage of 9 volts with a lab bench power supply and use this resistor with 5 rings right here. Now first we have to determine the resistor's value. Let's first orient the resistor so that the ring with the largest spacing is on the right. Then we have a brown ring, 3 black rings and another brown ring. The first 3 rings are the digits, in this case 1, 0, 0, while the 4th ring is the multiplier. In this case it is 10 to the power of 0, so we get a resistance value of 100 ohms with an accuracy of ±1% as defined by the last brown ring. Let's measure that with our multimeter. A multimeter is a measurement instrument with which you can measure many different electrical properties such as voltage, resistance, conductivity and more. A multimeter is a highly recommendable tool for electronic enthusiasts as it helps to troubleshoot your project and is cheap to access. We can calculate the current and get I is equal to U over R, which is equal to 90 milliamps. Let's test if this calculation applies in reality as well. As you can see, we plug the resistor into a breadboard and use jumper cables to connect the resistor to the crocodile clamps of the lab bench power supply. Our lab bench power supply has a beneficial feature that we can adjust the voltage according to our needs. Further, it incorporates an ammeter to measure the current flowing in the circuit. As you can see, the lab bench power supply indicates a flowing current of 0.09 amps, which is exactly the current of 90 milliamps we expected. So, the proportionality constant of voltage and current is called the resistance and is given in ohm. We can compare the resistance to the diameter of a water pipe, which, in combination with the height difference of 2 poles, determines the flow rate of the water. Ohm's law states that the relationship between the voltage and the current is called the resistance. Every component, even a wire, has some resistance, and sometimes we even want to introduce resistance intentionally, which is when we have to use a resistor. The first 2 to 3 rings represent the digits of the resistor value, while the second last ring provides the multiplier and the final ring provides the tolerance. We can illustrate the wiring of our components by a schematic with the specified symbol each component has. A battery is indicated by a symbol with a longer and a shorter line, where the longer line represents the positive terminal and the shorter line represents the negative terminal. A resistor is represented by a rectangle with 2 leads extending from either end. By connecting the different symbols, we indicate how they should be wired when building the physical circuit. We can calculate the current that flows in a standard battery resistor circuit by using Ohm's law. The full course is available on Udemy.